In this problem, we have a rock that is dropped from a height of 100 feet, and its position function, t seconds after it is dropped, is given by s of t equals negative 16 t squared plus 100. And we're first going to find out how long it takes before the rock hits the ground. We're going to find the average velocity of the rock between the time the rock is released and the time it hits the ground, and then we're going to find the time t that is guaranteed by the mean value theorem, where the instantaneous velocity is equal to the average velocity of the rock. And so first we'll review the mean value theorem. So here's a picture to help us understand better the mean value theorem. And we can think of the mean value theorem basically as a slanted version of Rolle's theorem. So remember, Rolle's theorem said that f of a and f of b had to be equal. So that means that the line connecting them had to be horizontal, right? Now we're looking at, here's a, and so f of a is here, and here's b, so f of b is here. And so if you look at the secant line connecting them, it's no longer horizontal. But what the mean value theorem tells us is that there's some point C, at least one, there could be more than one, such that the slope of the tangent line at that point is equal to the slope of the secant line connecting those 2 points. All right? So how do we find out how long it takes before the rock hits the ground? What do we know about the rock when it hits the ground? We don't know anything about the velocity yet, so the only thing we know is that the position is going to be 0 when it hits the ground. So the way we'd find that out is we would set the position function equal to 0 to find out the time at which it hits the ground. So the first step is to subtract 100 from both sides, and I get negative 16 t squared equals negative 100. Divide both sides by negative 16, and that gives me t squared equals 6.25, and then t has to equal plus or minus the square root of 6.25, which is plus or minus 2.5. All right, and we can't have a negative time, so t equals 2.5 is when the rock hits the ground, after 2.5 seconds. So t equals 2.5 seconds is when the rock hits the ground. All right, now we want to find the average velocity of the rock between the time the rock is released and the time the rock hits the ground. So to find the average velocity, remember we take the change in position. So we want to take the position after 2.5 seconds. Actually, we should call that s of 2.5 because that's our position function. So s of 2.5 minus s of 0 all over 2.5 minus 0, so all over the change in time. So that is s of 2.5, plugging it in here, is negative 16 times 2.5 squared plus 100. And then s of 0, we're subtracting s of 0, and that's going to be just, if we plug 0 in there, we're going to get negative 16 times 0 squared, and then plus 100. All right, and that's all over 2.5. So let's do the math. And I'm getting this first number to be 100, or negative 100 plus 100, and then the second part is going to be negative 100 all over 2.5. And these two are going to cancel each other out, so we get negative 100 over 2.5, which is negative 40. All right, and that's in feet per second. Don't forget our units. All right, so the average velocity of the rock is negative 40 feet per second, and we're trying to find the time guaranteed by the mean value theorem when the instantaneous velocity equals that value. All right, so to find instantaneous velocity, remember we need the derivative. And so that's just the derivative of the position function, and that's going to be negative 32t, isn't it? Simple derivative. All right, and we want to find out where that is equal to negative 40. And so we divide both sides by negative 32, and we get 1.25. So after 1.25 seconds, the instantaneous velocity will be negative 40 feet per second. All right. So that's our answer.